Hello. Today we're going to look at section 7.3, which is trig substitution. It's pretty closely related to what we did last time, which was trig integrals. So make sure you've really gone over section 7.1 and 7.2 before trying this, because it piggybacks on a lot of the concepts from those two sections. So let's get started. So the type of substitution that we're going to make is called an inverse substitution. Inverse substitution basically means we do a substitution backwards. So we've seen, for example, when you see this thing on the right, this would be like a u substitution, and you try to simplify an integral so you can do it. What we're going to do here is the opposite of that. We're going to be given an integral that looks pretty nice, and then we're going to expand it into a product. And I'll show you how that works. So here are some forms. So anytime things that look like one of these three things pop up in an integral, then it's possible that you're supposed to use these substitutions. It's not a guaranteed one-size-fits-all method, but it's a method that could work for different types of integrals in general. So it'll work for all the ones in this section. So for example, if we have an integral that looks like this, then you just automatically write this substitution. And what we use then is that there's lots of identities. So these are all Pythagorean identities. So you use these identities to change the integral to make it not only easier to do, but to make it possible to be solved. And as you can guess, it uses a lot of trigonometry. So let's get right into it. So thinking about the techniques we have so far, from Calc 1 and Calc 2, you have power rule, u substitution, things like that. You have integration by parts. None of those techniques will work on this problem. There's just no way to get it done. It's just too hard. But because it has this form in the denominator, it has the form square root of x squared plus a squared, that tells us that trig substitution is going to work because we've tried the other ones already. Right? And that's what this says. So the substitution, find a, so here's a squared, so it's 4. So a is 2. And you just write x equals a tangent theta. So use that table from a couple slides ago. You're going to use that table to do all the problems in this section. And then you want to write it like this. And I'll show you in a second why you want to write it like that. So this is the substitution, and then you solve it for the trig function. And then you take the differential. You can do either one. You can take the differential of either one. It doesn't make any difference. Generally speaking, though, if you just look at the problem and see what we have, this problem just has a dx by itself. So you want to take this differential because you've got a dx by itself. So what we're going to do is, everywhere we see an x, we're going to plug in 2 tangent theta. Everywhere we see a dx, we're going to plug in 2 secant squared theta, d theta. But before we do that, we have to draw a triangle. It doesn't matter when you draw the triangle, but drawing it early is better. So see here that we have x over 2 as tangent theta. So in this right triangle, tangent of theta is opposite over adjacent, x over 2. So you saw how to do this in trigonometry or pre-calculus. It's possible you forgot how to do it, but you're going to have to draw these triangles, and you're going to have to find the side lengths, or you won't be able to solve most of the problems in this section. And trig substitution comes up a lot in this class. As we moving forward, it comes up a lot. So you just use the Pythagorean theorem to finish the triangle. It's no coincidence that the missing side length is exactly the denominator. That pretty much always happens. And make sure that you can draw these triangles. All right, so on the next slide, we're going to plug this expression in for x, and then we're going to plug this expression in for dx. So as you can see, there's going to be a lot of simplification. So simplify as much as you can. So the first thing I did here, I pulled this 2 to the front. I cubed this. I squared this. And I brought the secant squared d theta, I brought the secant squared into the numerator. So as I'm going through these steps, if you need to pause the video and verify that you can do this, some of these problems take a really, really, really long time. But that's okay. You just got to practice it and you'll be able to do it. So I factored a 4 out of this denominator. When it comes out of the radical, it becomes a 2. And I combined the 8 and the 2 to get a 16. I didn't do anything else. Now I use the identity from a few slides ago that I need this expression under the radical to go away. So tangent squared plus 1 is secant squared. Then I canceled this 2 and this 16 to make an 8. Square root of secant squared is just secant theta. You don't need the absolute value there. A lot of times in algebra, if you square something and then take the square root, you need the absolute value. You don't need it for these. I explain in a few slides why you don't need it for these. Now you can see what we have is a secant squared on top of a secant, so we're going to cancel that. And you can see that as we simplify, it starts getting more and more manageable. That's the idea. And in section 7.2, we saw how to solve this. If you have odd powers of secant, you pull out a secant tangent, right? So here we just have one secant, so it's already out. But we take one more tangent and bring it out. Then those tangent squareds turn into secant squareds minus 1. And from here, it's just a u substitution. Because here's the derivative of u, and u will just be secant theta. So what we did is we did an inverse substitution. Now we're doing a u substitution. If you were able to see all the way through these problems, you could have done the u substitution at the very beginning, but we need to manipulate it enough that you can see what the solution method's going to be. It's not clear-cut when you first start that this thing's going to end up u squared minus 1. Because when you see it in the beginning of the problem, it sure doesn't look like that. So here's u squared minus 1. Here's du. Plug everything in. That's a really easy integral to do. Now we have to do the substitutions in reverse order. So we have to replace u's with thetas again. But we have to replace these secant thetas with the sides from our right triangle. When we started this problem, our substitution was tangent theta, which is opposite over adjacent. Now it's secant theta, which is hypotenuse over adjacent. So if you don't figure out that the length of the hypotenuse, you can't finish these problems. Luckily, we know the length of the hypotenuse. We computed it. So anytime I see a secant, I'm going to replace it with hypotenuse over adjacent. Right? So 8 times a third, secant cubed. So it just becomes secant of theta is just that over that. Cube it. minus that over that. Don't cube it. And then you want to simplify as much as you can. In the numerator, this is 4 plus x squared to the 1/2 power to the 3rd power. So that's 4 plus x squared to the 3/2 power. This 2 is also cubed, so it becomes an 8 in a denominator. So this 8 in the denominator cancels this 8. So those 8's go away, and you're just left with the expression you see here. The only other thing I did is distribute this 8 into here, and the 8 and the 2 cancel down to a 4. So this is a pretty typical problem of its type. There's 3 different types of problems you see in trig substitution. This is one of them. All right. Now let's look at a different type of problem. So definite integrals with trig substitution are actually very different than normal definite integrals. And it's because the substitution, because it's an inverse substitution, when you change the limits of integration, you have to do it as an inverse change. So for example, if we're plugging in, this substitution for tangent theta, when you change the limits, it's arctan when you figure out the limits. And that's why we have to worry about these domains. So one more note about the domains. All of these functions are 1-to-1 on their domains. That's why you don't need the absolute value, because each y value happens exactly once for each x value. So if you input a negative number, you get back out a negative number. If you input a positive number, you get back out a positive number for sine and tangent. Secant is an even function. So even if you plug in negative numbers, you get positive numbers back out. That's why its domain looks so funny. Because you're probably looking at this domain saying, this is really weird. But these are the 2 places where arcsecant is 1-to-1. All right. So let's do a definite integral problem. Again, another typical type of problem. We have the form a squared minus x squared, so we're going to use, right, it has this form, so we're going to use x equals 1 sine theta, right? A is 1. And dx is just the derivative. And then you just plug everything in. But before we do that, we have to look how this substitution is going to affect these limits of integration. So these functions are invertible on their domains. From the previous slides, I gave you that little domain on the side. So really what you're doing is you're saying, I need to change these limits to theta. So you say to yourself, well, where is sine of theta equal to 0? So you're really just taking the arcsine. You don't have to do it that way, but it's basically what you're doing. So arcsine of 0 is 0. Arcsine of 1, so where is sine of theta equal to 1? It's at pi over 2. All right? So if you don't want to use the arc functions, that's fine. If you just want to think of it like on the unit circle, if that's easier, go ahead and do it that way. Because we're going to be in quadrants 1 and 4 mostly, but we could be in quadrants 1 and 3. So here's our original integral. Here it is after the trig substitution has been made, right? Arcsine of 0 is 0. Arcsine of 1 is pi over 2. And you can see that x equals sine, so this is sine cubed, 1 minus sine squared. And then dx is cosine theta d theta. So in the next slide, I just replaced this. So if you go back to one of the earlier slides, I had the identity that you use. Every time you plug in x equals a sine theta, you're going to use this identity to turn these sines into cosines. And after seeing the last problem, you're probably starting to see it. We need whatever's under this radical to match up with what's over here. So here it's 1 minus sine squared, which becomes cosine squared. Well, square root of cosine squared is just cosine times cosine is cosine squared. So you can see it always simplifies real nice. From here, we know how to do this problem. Sine is to an odd power, so we want to pull out one copy of sine. Then we want to use Pythagorean identities to turn this sine squared into cosine squared. And then you want to simplify. You want to bring all the cosines together. So distribute here. Right? So let me go back one slide, show you. Cosine squared times 1 is cosine squared. Cosine squared times cosine squared is cosine to the 4th. Now it's a U substitution. And this is negative sine theta. We have sine theta, so it's just going to put a negative in front of the whole thing. And we have to change the limits of integration again. But this time you're just plugging it in, right? Cosine of 0 is 1. Cosine of pi over 2 is 0. So our limits of integration turned back into the original ones. That's a coincidence. That doesn't always happen. And I have the bigger number on the bottom. I'd like to have the bigger number on the top, so I'm going to switch those. When you switch these limits, it gets rid of the negative or puts a negative if there isn't one. From here, it's a relatively straightforward U substitution. But it's a definite integral, so we can just evaluate it. We don't have to put it back into its original form. So a quick note about how you know when to do what with a definite integral with two substitutions. If you don't like this method, you don't have to use it. You're allowed to do what we did in example 1 and go from u back to theta, back to x, and then plug in the original limits. That's totally fine. You get the exact same answer. But I think this is a little bit faster. It's less algebra. So if you have the ability to do it this way, I think this is the best way to do it. Keep changing those limits of integration. And then as soon as you get to the u substitution, you're done. Or the integral of the u, you're done. All right, let's talk about one more type of problem. And it's what happens when we have completing the square. So it turns out that we can use trig substitution to solve this. It doesn't look like we can, but we can. What we want to do is complete the square on this quantity. Here's how you complete the square. You set the entire integrand equal to 0. Like what's under the radical in the integrand, set it equal to 0. Then you move the constant to the other side. So what I did, I just reordered this because for me it's easier to factor things where the x squared is on the left. So all I did is pulled this negative out. So negative x squared, negative 12x is positive x. I just factored a negative out so I could reorder it. And likewise, when this comes to the other side, it's also negative. Then what you do for completing the square, do it inside the parentheses. You cut this coefficient in half, whatever's times x, cut it in half and square it. So half of negative 12 is negative 6. Negative 6 squared is 36. So you add half of this to both sides. Here, it looks like I'm adding a positive number. It's not, because the minus is on the outside. So inside the parentheses, you write it positive, but we're really adding a negative 36 to both sides. So when you do it over here, I went ahead and put it inside some parentheses so I can remember it's negative 36. If you want to write negative 36, that's fine. But I like to kind of just keep track of everything as I go. So this is a perfect square, right? It's just the square root of this minus the square root of this. You can FOIL it out if you want to, but that's how it works. And this just becomes negative 49. And then there's one more step. You bring the constant back over to the other side. So add 49 to both sides and you're done. So this quantity here is the same as this quantity here. And you can FOIL this out and check that it works. So in this problem, we're going to evaluate this integral. And we're just going to replace it with its completing the square version that we just figured out. Again, you want to do that as side work. Don't do that under the radical because you're going to end up writing things down that you're not allowed to do. So like set this problem aside, do some side work, and then put it back inside the radical. So what we have here is you match up the form. This looks like an a squared minus u squared. Right, so this looks like that sign substitution again. And the idea is just if we let u be x minus 6, this is a squared minus u squared. So you don't actually have to do the u substitution. Right, now we're still doing the trig substitution, but we're not, at this stage, we're not actually doing a u substitution. I'm just showing you the form. As soon as you're able to draw the triangle, it turns into just a normal calculus problem. So our substitution is going to be x minus 6. So this whole thing inside the square root, we're going to call 7 sine theta, right? Because it's a squared is 49, so a, what we're calling a, is 7. And then you get the trig function by itself to draw the triangle. And when you take the differential, do it from here. So the derivative of x minus 6 is just dx. And the derivative of 7 sine theta is 7 cosine theta d theta. So there's your triangle, right? So sine theta is x minus 6 over 7. It's opposite over hypotenuse. X minus 6, 7. Again, as we saw in earlier problems, the missing side of the right triangle is this. That's what we want. So if you build these triangles correctly, when you find that missing side, it'll be this. Now we do the substitution with x minus 6 is equal to 7 sine theta. Our dx is 7 cosine theta d theta. This one's a little easier to simplify than earlier problems. So I just took this 7 and brought it to the front. Here we have 7 squared, which is 49, so I just factored the 49 out. Square root of 49 is 7. 7 times 7 is 49. 1 minus sine squared theta is cosine squared theta. And square root of cosine squared is cosine. Cosine times cosine is cosine squared. But we get to this part of the problem, and it looks like we're stuck, because we don't have a rule for cosine squared. What we saw in section 7.2 is if you have combinations of sine and cosine that appear together, this is a cosine squared by itself. We do this particular integral a whole bunch the rest of the semester. Cosine squared just pops up naturally. So this is how you do it. You replace this with the identity. 1/2 cosine squared is 1/2 times 1 plus cosine 2 theta. And then d theta just stays d theta. And then you simplify a little bit. And then you do the integral, right? So I simplified, I brought the 1/2 to the front. Then the integral of 1 d theta is theta. Integral of cosine of 2 theta is 1/2 sine 2 theta. This technically is a u substitution. You should be able to do this particular step I remember talking to folks in your class when I was first talking to you with either in-person or Zoom meetings, and I brought up stuff like this, like can you do certain integrals in your head? This is the kind of integral you want to do in your head, because we're about halfway done with this problem and it's still already a very long problem. So again, if you're like, well, why is the integral of cosine 2 theta 1/2 sine 2 theta? It's because the derivative of this is that. Remember, if you know how to do derivatives, then you know how to do integrals. So the derivative of sine of 2 theta is cosine 2 theta times 2. The 2 and the 1/2 cancel. So when we go the other way, you need to divide by what the chain rule would give you. Okay, so I distributed the 49 fourths, right? So if you look here, I'm sorry, the 49 halves. 49 halves times theta is 49 halves theta. And then distribute this into the 1/2, you get 49 fourths. But we're stuck again. Our right triangle gives us information about theta, not 2 theta. So we have to use another trig identity. You're going to be doing these identities enough that you should just memorize them. And those are coming up on a slide. There's like a list of the 4 that you want to memorize, if you haven't already. So in that last step, I just simplified this, right? The 2 and this 4 cancels down to a 2. Now we throw our triangle back up there. Notice that we started off with sines, but now we have sines and cosines. So sine theta, we already know is x minus 6 over 7. Cosine theta is this expression over 7. And now we actually have a theta here as well. Theta is the angle, but we need to turn it into x's. So you just use whatever your initial substitution was, but do it as an arc function. So our initial substitution was sine theta. So theta then is arc sine. So if I've gotten to this step and you don't remember all of this stuff, you're going to want to pause as soon as this problem is done and go back and look at that stuff again. I do a pretty good treatment of this back in section 6.6, so make sure you go back and look at that. So it's arc sine of x minus 6 over 7. Here's sine theta, here's cosine theta. You don't need to simplify under the radical. You can if you want, but you just don't need to. But you do want to simplify things like denominators, constants, things that drop out. So what we have here is a 49 divided by 7 divided by 7, so that all those go away. We're left with this 2 in the denominator, and then we're left with both of these numerators. And that's the answer. All right, got one more thing to talk about in this section, and then I'll let you go. Like I said, if you're struggling with all this trigonometry, go back and look at section 6.6 from a few weeks ago. So it turns out trig substitution is not always the best method. You can see that there's this integral down here, and you see that square root, and you think, oh, that's a tangent substitution. But it turns out for this particular problem, it's much easier as a u substitution. So u substitution is better. If you're not sure what to try, at least try a u substitution first. If you can't figure one out or it doesn't work, then trig substitution will always work if it looks like this. But as you can see, these are very long problems. So you don't want to do a method with 15 steps if you can do one with 4. That's the idea. All right. Well, that's it for this video. If you have any questions, as always, just get a hold of me or post something on the message board. And that's it for today, and I'll see you all later. Bye-bye.